Hello, welcome to Lesson 2 on Gates and Circuits. My name is Dr. Ritesh Ajoodha. At the end of this lesson, you should be able to describe the behavior of circuits using Boolean expressions, truth tables, and logic diagrams. You should be able to prove the basic properties of Boolean algebra, manipulate expressions using Boolean algebra, and finally, design a half adder and a full adder. So what is a circuit? A circuit is a combination of gates to complete a more complicated task. There are two types of circuits: combinational circuits and sequential circuits. In combinational circuits, the output values are determined explicitly by the input values. In sequential circuits, the output value is determined by the input value as well as the existing state of the circuit. In this video, we will be focusing on combinational circuits. Consider the following combinational circuit, where A, B, and C are input variables. A and B goes into an OR gate. The output of this OR gate would be A or B. B and C go into this OR gate. The output of this OR gate will be B or C. Finally, the output of this OR gate and this OR gate go into this AND gate, and the output of this AND gate will be A or B and B or C. We can explicitly state all possible input and output relationships concisely in a truth table. Consider the following truth table, where A, B, and C are input binary variables. These are all of the different combinations of input that are possible for this particular circuit with three binary variables. We can now fill in the column for A or B, which would be the output of this gate. B or C, the output of this gate, and A or B and B or C, the output of this AND gate. For more information on how these logical operations work, have a look at the previous lesson. It is possible that two differently constructed combinational circuits can give us the same input and output description. Have a look at these two combinational circuits. In this combinational circuit, we see that A and B go into an OR gate. The result of this OR gate goes into another OR gate with C, giving us A or B or C. In this OR gate, we have B and C, the result of which goes in another OR gate with A, giving us A or B or C. We see that these two combinational circuits are constructed differently, but according to this truth table, they give us the same result. This is known as circuit equivalence. As a consequence of circuit equivalence, certain properties of Boolean algebra can be established. Here is a list of 7 properties of Boolean algebra. Let's begin with commutativity. The commutative property states that if you have two binary variables A and B is equal to B and A or B is equal to B or A. In associativity, we have 3 binary variables, A, B, and C, which states that if you group A and B and then AND that by C, it will be the same as saying A and the grouping of B and C. The distributivity property is more interesting. It states that if we have 3 binary variables, then A and B or C is equal to A and B or A and C. Similarly, for the OR gate, A or B and C is equal to A or B and A or C. The identity property states that if you have a binary variable A and a column full of 1s, this would just result in an A. If you have a binary variable A and a column full of 0s, if you OR these two, you would just have A again. The complement property states that if you have a binary variable A and if you AND it with A naught, you would get a column full of 0s. If you have a binary variable A and if you OR it with A naught, you would have a column full of 1s. The De Morgan property is an interesting and celebrated idea. It states that if you have A and B naught, this would just become A naught or B naught. Similarly, if you have A or B naught, this would simply become A naught and B naught. The last property is called absorption. It states that if you have A or A and B, this would just be A. If you have A and A or B, this would just be A again. You might find this property to be very useful. Let's try to prove the absorption property using a truth table. We can break up certain parts of this expression into columns in this truth table. Let's break up this expression by narrowing into the parenthesis A or B. So we can have a column for A or B and another column for the entire expression, which is A or B, this column, ANDed with A, this column. Since we already have a column for A, we don't need to have another one. This leaves us just to fill in the cells for A or B, and then looking at this column and this column, A and A or B. We now prove this expression since this column is exactly the same as this column, which indicates that A and A or B is equal to A. Now that we know how gates work, how to construct circuits, and the basic properties of Boolean algebra, let's try to put our theoretical knowledge into practice by building a binary adder. Suppose we want to add two digits, A and B. If they are just two digits, then there are four different scenarios that we could be faced with. We could be adding A is equal to 0 to B is equal to 0, which gives us a 0. We could be adding A, which is equal to 0, and B, which is equal to 1. We would get a 1. In the third case, 1 plus 0 would give us a 1. And in the fourth case, 1 plus 1 gives us a 0 with a carry. We can visualize this using a truth table, where A and B are the binary random variables, and A plus B represents the sum, and the column carry represents if we have a carry or not. We can then just represent the information of the addition of the two digits and the carry onto this table. Now that we have this information, we can analyze it. We see that the A plus B column looks exactly like the behavior of an exclusive OR gate, and the carry column looks exactly like the behavior of an AND gate. If we put these gates together with the binary random variables A and B, we get a circuit which does this addition in binary with two digits. A and B goes into an exclusive OR gate to give us the column A plus B. And A and B also goes into an AND gate to indicate whether a carry is necessary or not. Now that we've designed our half adder, let's try to construct a full adder. The full adder considers the situation where we have a carry in. As an example, consider the addition of these two binary numbers, 01 and 11. If we were to add this column, 1 plus 1, we would get a 0 with a carry. We would have to then consider the carry in from this column when we're doing the addition on this column. That means we would have to now say 1 plus 0 plus 1 to give us 1, 0. That would require us to export a 1 to the next column, and that column will have to now incorporate that 1 into its addition. The full adder accommodates this by having another input, SC in, being whether there was a carry in or not. Let's now complete this table. In this table, to get A plus B, we would have to consider whether there was a carry in. So in the first row, A is 0, B is 0, and C is 0, which means there was no carry in. Therefore, A plus B plus C would be 0 with no carry out. The second column, we add 0 plus 1, which gives us 1 without a carry. 0 plus 1 plus 0 is 1 without a carry. 0 plus 1 plus 1 is 0 with a carry. 1 plus 0 plus 0 is 1 without a carry. 1 plus 0 plus 1 is 0 with a carry. 1 plus 1 plus 0 is 0 with a carry. 1 plus 1 plus 1 is 1 with a carry. Now we have the following table, where A, B, and C are input variables, A plus B is the output, and C out is the output. Our goal now is to convert this truth table into a circuit diagram. A circuit diagram that takes A, B, and C in as inputs and outputs A plus B and outputs C out. We can convert a truth table into a Boolean expression using the disjunctive normal form algorithm. And from the Boolean expression, we can then construct the circuit diagram. The disjunctive normal form algorithm is a three-step process. The first step is to write a star on the row wherever you see a 1 output. Since we want to convert this A plus B as an output variable, we can write a star wherever we see a 1. So we'll put a star here, 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 and here. The second step of the disjunctive normal form algorithm is to conjunct the input variables from left to right, wherever we have a star. So, looking at our first star, we will conjunct the input variables A, B, and C in, which we will now refer to as C, just for simplicity. So, if A is a 0, we will represent A with a naught. And if A was a 1, we would represent it just as A. So if we conjunct from left to right, we would get A naught, B naught, and C. For this column, we'll get A naught, B, and C naught. For this column, we'll get A, B naught, and C naught. And finally, for the last column, we will just have A, B, and C. The third and final step of our disjunctive normal form algorithm is to simply disjunct or OR the output variable from top to bottom. Since A plus B is our output variable, we will OR each of these expressions to give us one large expression. That results in the following expression: A naught, B naught, C, or A naught, B, C naught, or A, B naught, C naught, or A, B, C. If we were to construct a circuit diagram using this expression, we would need a lot of gates. Just at a glance, we would require 1, 2, 3, 4, 5, 6, 7, 8 AND gates, 1, 2, 3 OR gates, 1, 2, 3, 4, 5, and 6 NOT gates. That's a lot of gates for this expression. We can use the properties of Boolean algebra to simplify this expression so that we use less resources to construct the circuit. So let's consider manipulating this expression using the properties of Boolean algebra. At a quick glance, we notice that A naught is common in the first term and the second term. We also notice that A is common in the third term and the fourth term. That means we can use the distributive law to pull out A naught from the first and second term, and again use the distributive law for the third and fourth term to pull out A. There's something interesting about this term, B naught C or B C naught. It suggests that the output would be true if B and C are different. That sounds familiar. It sounds like the exclusive OR gate for B and C. We can substitute B exclusive OR C in place of this expression, which leaves us with the following expression. Upon closer inspection, we see that the term B naught C naught or BC also sounds familiar. This suggests that it'll output a 1 if B and C are both the same. That sounds like the exclusive OR 2 put through a NOT gate. If we put an exclusive OR through a NOT gate, we will get, as this expression describes, a 1 if B and C are the same, and a 0 otherwise. So we can substitute B exclusive OR C naught in place of B naught, C naught, or BC. That gives us the following expression. We've already seen that we've reduced the number of gates substantially from our first expression to this expression by just employing some basic rules of Boolean algebra. In situations like this, it might become difficult to identify aspects which can be simplified if we have many repeating terms, which become distracting. So, if we substitute this large term B exclusive of C, which appears twice in this expression, with a smaller term, let's say K, we might be able to pick up more simplifying factors by substituting K, which is equal to B exclusive of C. Let's see what we get. Already we notice something quite interesting. If we substitute K, we notice that we get another exclusive or term, which we've seen before when we looked at B naught C or B C naught. Now we have A naught K or A K naught, which is exactly the same as an exclusive or with A and K respectively. So we can substitute our A naught K or A K naught with A exclusive or K. But K is equal to B exclusive or C, so we need to substitute that back in, which gives us A exclusive or B exclusive or C. Finally, our term A plus B can be represented by this expression, and we can use the associative rule to move the brackets from the B exclusive or C to the A exclusive or B. We can easily draw a circuit diagram for this term, compared to before when we had this larger term. If we just have two gates, A exclusive or B and A exclusive or B exclusive or C, we can just represent it using two exclusive OR gates, where A and B goes into an exclusive OR to give us A exclusive OR B, and the output of this exclusive OR goes into another with C in to give us A exclusive OR B exclusive OR C in, which is our A plus B term. We now need to go back to our table and work out what C out will become. So pause this video and try to follow the steps that I just did to try to get A plus B. But this time, do it with C out. You should have gotten the following term for C out: A naught B C, or A B naught C, or A B C naught, or A B C. Well, looking at the first two terms, we see that C is common. Let's pull out C as a common factor. We can do this using the distributive property. Looking at the last two terms, we see that AB is common. So let's pull out AB as common using the distributive property. Again, A naught B or AB naught looks exactly like an exclusive OR, and so we can easily just substitute A exclusive OR B for this term, as we've done so before. Notice that I'm giving a reason after each time I manipulate the expression. I expect you to do the same. The next term, AB into C naught or C, we notice that C naught or C looks a lot like the complement term, where we have A or A naught, which gives us a 1. So we can substitute a 1 using the complement property. Thereafter, we need to get rid of this 1 by using the identity property. Finally, we have C into A exclusive or B or AB. And this is the simplest form we can get it into. Remember that we need to build the C out on top of the circuit that we built for the sum. So let's put down the circuit for the sum. If you remember, it was A and B into an exclusive OR, which goes into another exclusive OR with C in to give us A exclusive OR B exclusive OR C in. Building on what we already have, we can have C and A exclusive OR B as taking C with this line over here. That gives us C, A exclusive of B. And then we can generate this term, which is just an A and B, taking our line A and B into an AND gate. And finally, combining this first term with the second term using an OR gate. That means taking the output of this AND gate and the output of this AND gate and putting it into an OR gate to give us the final term, C into A exclusive of B, or AB. And that's it, we're done. This is the circuit diagram for the full adder. Notice that the sum of A, B, and C in come out to this line, and is represented by this expression. And the indication of whether there's a C out or carry out comes out to this line, and is expressed by this expression. To solidify your understanding of the concepts presented in this video, I'd like you to try the following 4 exercises. Number 1. Prove the distributive and De Morgan properties using a truth table. Thereafter, prove this expression by manipulating either side, the left-hand side or the right-hand side, using the properties of Boolean algebra, which I presented in this video. Then, now that you've learned how to build a half adder and a full adder, try your luck with a half subtractor or full subtractor, and try to generate both the truth table, the Boolean expressions, and the circuit diagram for both of these. Finally, use the disjunctive normal form algorithm on the output variable x, which is this column, to convert the following truth table into a circuit diagram. Try to use as fewer gates as possible by simplifying the expression as much as you can.